Hey everyone, and welcome. Today, we're going to go on the incredible secret journey that sound takes, from the real world all the way into your headphones. Let's dive in.
So, have you ever really stopped to think about it? How does a physical sound, something you can feel, become a file that you can just send anywhere in the world? It seriously seems like magic, but it's actually this fascinating mix of physics and computer science.
All right, so first things first. Before any sound can become digital, it has to be captured. And that whole process starts with understanding what sound actually is. It's just a vibration traveling through the air.
Every single sound you hear, your voice, a clap of thunder, music, it's what we call an analog signal. The best way to picture it is as a smooth, unbroken wave. You know, in the real world, sound doesn't have any breaks or gaps. It's just this continuous flow of energy.
So how do we grab that wave? Well, that's where a microphone comes in. A microphone basically works like a mechanical ear. That wave of air pressure hits this tiny, really sensitive part inside called the diaphragm, and that makes it vibrate. The microphone then takes that physical movement and turns it into a changing electrical voltage, an exact electronic copy of the original sound wave.
Okay, so we've got this sound captured as an electrical wave. Now we're at a really key moment, the point where we leave the physical world behind and jump into the digital one. How does that smooth wave become something a computer can actually read?
This whole magic trick is called analog to digital conversion. A special little chip called an ADC rapidly measures the wave's voltage thousands of times per second. It's kind of like if you were trying to trace a smooth curve by plotting thousands and thousands of tiny connected dots. What you end up with is a perfect numerical map of that original sound.
And then, those numbers are translated into binary code. So your favorite song, sitting there on your phone, it isn't actually music at all. It's just an incredibly long, super detailed sequence of ones and zeros that the computer knows how to read. Kind of wild, right?
So what makes one digital file sound amazing and another one not so great? Well, it all comes down to two key factors that act like its digital DNA: sample rate and bit depth. Okay, sample rate. This tells us how often the converter is taking those snapshots. It's a lot like frames per second in a video. The more snapshots, or frames, you take, the smoother and more accurate the final digital version of the sound is going to be. And to give you an idea of just how precise this is, a standard CD quality sound is measured over 44,000 times every single second. For professional recordings in a studio, that number can jump to 96,000 times a second, just to capture every last detail. Right, so if sample rate is how often you take a snapshot, bit depth is how much detail is in each of those snapshots. It's like deciding if you're going to draw a picture with a box of 8 crayons or a giant box with 64. More bits mean you have way more values for loudness in each sample.
And the difference here is huge. 16-bit audio, the CD standard, gives you over 65,000 possible volume steps. That's pretty good. But 24-bit audio, which is what they use in studios, has over 16 million. This massive range means it can capture everything from the quietest little whisper to the loudest possible explosion with amazing accuracy.
So all that incredible detail from high sample rates and bit depths, it creates absolutely enormous files. The next big challenge is, how do we make them small enough to stream online or fit thousands of them on your phone?
I'm sure you've seen these file types before. WAV files are the raw, uncompressed originals. Perfect quality, but they are massive. MP3s are the ones we all know. They're compressed to be small and easy to share. And then you have formats like FLAC, which are cleverly compressed so they take up less space, but can be unpacked back to their original perfect quality.
This compression comes in two main flavors. Lossless is basically like a zip file for your audio. It packs everything down without throwing anything away. But lossy, which is what MP3s use, is different. It uses some really smart algorithms to permanently delete sounds that are very high, very low, or are being masked by louder sounds. Basically, stuff your ears probably wouldn't have noticed anyway. And that's how it makes the files so much smaller.
So we've gone from a sound wave to a tiny digital file. But how does that file become a vibration we can hear again? Let's check out the final step in this amazing journey.
When you hit play, your phone or computer does that entire process, but completely in reverse. The ones and zeros are sent to a digital to analog converter, or a DAC, which reads that numerical map and perfectly rebuilds the original electrical wave. That electrical signal then travels to your headphones, makes the tiny speakers inside vibrate, and creates the sound waves that travel right to your eardrums.
And most modern music uses 2 channels, stereo, to make the experience way more immersive. By sending slightly different information to the left and right speakers in your headphones, producers can make it sound like the drums are on your right and the guitar is on your left, creating this awesome sense of space, almost like you're in the room with the band.
I mean, think about it. This incredibly complex journey happens every single time you listen to a song. It goes from a physical vibration to electricity to a mathematical code and all the way back to a physical vibration again, and it all happens almost instantly.
It's definitely something to think about next time you put on your headphones and press play. Now that you know the whole journey of a sound, will you ever really listen to music the same way again?